here is setting it up. In other words, defining your function that you're trying to maximize. Again, it's an area function, okay? An area is base times height. And this point right here is 3. In other words, our zeros of this function occur at 0 and 3. So now what's the base of my rectangle? What's this point right here?
We say 1.
X.
X.
Remember, I'm looking at all kinds of possible rectangles. I'm not just working with that first rectangle. I don't know the shape of the rectangle that I'm going to put in there. All I know is that point is X. That's where it's going to begin.
Okay.
And because of symmetry, this distance has to be X also. So now what is my base of the rectangle equal to?
2x.
No, I want the dimension from here to here. That's the base of the rectangle. 3 minus 2x.
Okay.
You see why? In other words, from here to here is 3. And my rectangle is everything except that x and this x. So it's 3 minus 2x is the base. Again, the height is y, and in this case, the height is this. So, same exact problem, but a slightly different take on how you define the base of the rectangle. All right, let's go focus on your problems. Now, this may not be the page you want to start on. Let's see. Did we finish this page?
Yes. I think I was going to ask you about number 6 too.
Goodness. Well, I guess the only thing we can try to do is draw a picture and figure it out. This is liable to take quite a bit. Are you sure this is what you want to spend the next 20 minutes on? For one thing, local linearization is, for some reason, a difficult model to understand. I've always had a little bit of problem with it. And you don't use it very often in calculus. But when you're going through this chapter, they do give it to you because this is the way they used to approximate stuff before they could do it. This is kind of an approximation method. Let me think. I'm not sure I can figure it out. Right off the get-go, let's see. If we write, we're going south to north. That's 420 miles. Without stopping. At noon, she notices her speed is 60 miles per hour at noon. And she is at mile marker 240. Here, let's label this 420 as the top label. In fact, yeah, that's 420. Okay? And And, okay. Use this data to write a linear function which could be used to estimate her position as a function of time, time being noon. Well, this doesn't seem that hard. In fact, it doesn't seem like a calculus problem. What am I missing here? If she's going 60 miles an hour, then hold on. She's noon is times 0. Well, approximate her position at 2 o'clock. Why is this not any? She's going 60 miles an hour. For 2 hours, she's going to go another 120 miles. So at 2 p.m., she's at the 360 mile marker. But that's algebra, not calculus.
Yeah. We can go to a different problem.
Her position at 10:30. Well, if I go backwards an hour and a half, she's going to go back 90 miles. So she would be at the 150 mile marker at 10:30. What is wrong with that analysis? Maybe that's all there is to this. Write a linear function. We haven't written the function yet. Well, her position along her route is 60 times t plus, why is it not just 60 times t if she's going 60 miles per hour? What is the domain on which your linear function can be applied? I don't know. I'm not getting this one, Jackson. I'm not seeing anything other than what looks like a straightforward algebra problem.
Yeah, it's fine. Do you have the next page?
Yeah, I do.
Okay. Can we do the graph at the top? Yeah.
Okay.
7 through 12.
Okay, so this is the graph of velocity, right?
Mm-hmm.
Acceleration is the first derivative of this graph. So look over at 5 seconds. What's the slope of this graph at 5 seconds?
Is it -3?
Uh-huh. And it's that slope from this point all the way down to this point. So we've got acceleration going on right here of -3 that entire time, not just at 5, but also between 4 and 6. Find the speed of the object at time 6 seconds. Well, speed is velocity without direction. That's the difference between speed and velocity. Speed is a scalar. It's just how fast you're going. Velocity is direction also. In other words, if I look at this chart here, I started out at a velocity of 1, positive 1, meaning I'm going to the right. Okay? And I'm going to the right all the way up here, and then finally right here I switch directions and I go to the left. Well, I'm still going to the left here. I don't get back to the starting position until right there. But speed is going to be the measurement, the absolute value of velocity. So what's the velocity at 6 seconds?
It'd be -3. So is it just 3?
It's just 3.
All right.
Okay. The velocity is -3, but the speed is just 3. On which interval of time is the object moving to the right? Looking at that graph.
You said from 0 to 5?
Correct?
Okay.
And moving to the left from 5 to 7. And the only reason we know is because that's positive velocity. And that's negative velocity. On which interval is the object's velocity increasing? Now this gets a little tricky. Let's start from the beginning. Is it increasing from 0 to 1?
Yes.
How about from 0 to 2?
Yeah.
And then it stays the same from 2 to 4. So you can't really say the velocity is increasing from 2 to 4. It's increasing from 0 to 2. And now it's decreasing, as well as speed is decreasing. In fact, the velocity is 0 right there, so it's stopped. Then it continues moving to the left at increasing speeds. In other words, here we're going 3 feet per second. Here we're going 2 feet per second to the left, 1 foot per second. We're stopped. Now we're going 1 foot per second. Excuse me, these speeds were to the right. Now we're stopped, and we're going 1 foot per second to the left. Now we're going 2 foot per second, 3 foot per second, still going 2 foot per second to the left. Okay, so at what time is the object furthest to the right?
5?
Yeah. It's moving to the right all of this time. And then all of this time it's moving to the left. So this has to be the point that it's the furthest to the right. Oh, yeah.
All right.
Okay. Which one next?
Maybe
Got about 10.
14?
Which one?
14?
Do they have any easy problems in your class?
I don't think so.
Actually, that last one was probably as easy as we're going to get.
Yeah.
Well, that thing should be the absolute value of minus x cubed plus 3x squared. Well, the intercepts aren't that hard. Let's ignore the absolute value for a moment. If I'm looking for the intercepts on that, I'm going to factor out an x squared. And I'm left with minus x plus 3. Okay? If I'm looking for intercepts, how do I find them?
So y equal to 0.
Correct. So what are my intercepts?
Would be 0 and let's see. Would just be 3.
Yep. Okay. the local extrema.
We have to find y-intercepts too?
Well, the y-intercept is 0. In other words, y-intercepts are when the, maybe, yeah, that's the x-intercepts, the y-intercepts. In other words, x-intercepts are when you set y equal to 0. Y-intercepts are when you set x equal to 0. In this case, when I set x equal to 0, I get 0. So this function goes through that point right there. It also goes through this point right here at 3. Now, to the left, x squared is always positive. Okay? Minus x plus 3 is going to be negative whenever x is greater than 3. So this function would normally, if I took away the absolute value of it, something like that. Does that work? Let's see. In other words, as x is 2, that's positive number, so we're going to be rising. And then as x gets to be 3, we get back to 0. And then as x gets to be greater than 3, this number is negative, this is still positive, so we have to be in negative territory. So I've effectively, and let's see, as x is negative, this is positive. So this thing looks something like this. Okay? And that looks more like a cubic function. That's without the square, without the absolute values. Okay? What does the absolute value do to this thing? In other words, you see why it rises up here? Because as x goes negative, this becomes bigger positive. This is always positive, so we got to turn around. We're only going to kiss the origin at that point right there. Now, how would I graph? In other words, what I have graphed is this. Okay? When I put the absolute value around it, how does that change that graph?
Everything's positive?
Correct. In other words, anything that's negative gets reflected, and it basically looks like that there. Okay, and not like that anymore. So now it's easy to see where the local extrema are. Where are they?
At 0 and 3.
Okay, that's two local minimums. Now, in order to find that, what am I going to do? In other words, I need the local maximum also.
You set the derivative greater than 0 or equal to 0?
Correct, and I can ignore the absolute value because I'm in the place of the function where the absolute value isn't going to matter.
Okay.
Okay, so all I need to do is take f prime and set it equal to 0. So f prime of x is what? Let's see, that looks like it must be minus 3x squared plus 6x. Did I do that right? Let's see, this is minus x cubed plus 3x squared. So the derivative of that is minus 3x squared plus 6x. And setting that equal to 0 will tell us where that point is on the x-axis. Well, I can factor out and setting it equal to 0. Again, I can factor out an x, and I get minus 3x plus 6. So there was 1, 0. We found that one. And this one is where x equals 2. So that's where that maximum is. Okay. And now points of inflection. Well, points of inflection are where concavity changes. Okay. Oh. Clearly here we're concave up. Clearly here we're concave down. And we're concave up there. So there should be a point of inflection there and a point of inflection there. How do we find?
Find the second derivative set equal to 0.
Correct. Minus 6x plus 6 equals 0. X equals 1. So that point of inflection comes at 1. Why did I only find 1 point? Must be all there is.
Okay.
Hold on. No, I'm not convinced that's all there is. Just, I know it's half an hour, but this just won't take me but a second here. I'm going to graph this thing on Wolfram Alpha. What was the function again? Absolute value. Let me graph it first without the absolute value. I know what the absolute value does. Minus x cubed plus 3x squared. So, notice what's happening. I get it now. When I plot the absolute value of this function, right there we have a reflection of everything below the axis.
So
we don't have concave up at any point in time. We have concave up over here. We have concave down right there. And 1 was the point where our inflection point turned out to be. That looks perfect. But notice this is all concave down, all the way down. And only when we put the absolute value in it does it take this curve, reflects it about the x-axis, and it goes straight up, and there is a cusp or a corner right there. Because there's a cusp, that is not concave up. And in fact, you can't differentiate across that point. So we never go from back to concave up.
Okay.
I'm trying to think, is if that thing's concave down and I reflect it, it's still concave down. Right? Yeah. In other words, if I have a, let's say, over here, I didn't draw the first curve right. I really drew it like that. It should be concave down the whole way, right?
Right.
And then when I reflect it, this thing merely goes like that. Nope, hold it. It goes the other way. It does. it's perfectly reflected, so it would be concave up. But that's still a corner or a cusp, and so we do go from concave down to concave up, but it's at a cusp. Now, whether that is a point of inflection or not, I'm not sure. We might have a point of inflection at 3 also. It's not that the second derivative is equal to 0 at 3. It's that the second derivative is not defined at 3. We can't even take the first derivative at 3. Because you cannot take derivatives at corners or cusps. So they're not defined. This one is not going to be defined at 3.
Okay.
We do go from a concave down to a concave up situation, but it's at a corner or cusp. And whether that's called an inflection point or not, I'm not sure. Anyway, I know you got to run. I'll let you go.
All right.
All right?
Yeah, thanks for clearing up the optimization. That was.
Yeah, those can be tricky, especially the one where you have the rectangle under the graph. Those are very tricky. So.
And then so next Friday I'll probably have my test back I just took yesterday. Go over that.
So we're just going to go with next Friday?
Yeah.
Okay. Then you got a final coming up shortly after that, right?
Yep.
Okay. So we'll probably do an hour next Friday?
Mm-hmm.
Okay. Sounds good. I'll talk to you then.
All right. Thank you.
Bye-bye.